One of the most important applications of calculus is finding areas under curves. And actually, just so you know, we didn't kind of do this out of nowhere. The area will be the antiderivative. We're gonna kind of put everything together in the next section. But right now, I want to kind of show you one way of finding the area under the curve, of estimating the area under a curve. Feel free to use a calculator for these because some of them have a lot of fractions that you have to add together. And I don't want you to be spending a lot of time dealing with fractions. So let's go ahead and first I want to talk about one thing. I'm going to give you a quick little example to try on your own based on what you know from geometry. And then I'll show you a different type of problem. So go ahead, see if you can find that yellow shaded area. Pause the video and try it. So I'm hoping that you figured out that that area is just an area of a triangle. One side is 3, one side is 3, the other side is 3. Area is 1/2 base times height. You get 9/2. Don't overthink that type of problem. Now, unfortunately, when we're finding areas, we're not always going to have something nice like this. Occasionally, we will get something curved. So, what do we do if a graph is curved? So in the first example, you had this nice graph. It's split nicely into a triangle. This one, however, if you look at that, it's really, really hard to find the area under that graph using geometry. So instead, what we're going to do is we can actually split this area into rectangles and add up all the areas of those little rectangles. Those rectangles are what we call Riemann sums. So there's a bunch of different ways of using Riemann sums, and I'll show you a few of them. So the first type of Riemann sum that we're going to talk about is what we call a left Riemann sum. And sometimes you'll also hear that called a lower Riemann sum. And basically what we do for a left Riemann sum is so I'll show you what I mean by Riemann sum. We're going to split this up into rectangles. Then we add up all of the sums of those rectangles. By the way, these don't look like rectangles, but use your imagination. Hopefully you're not drawing it with your fingers, so your rectangle looks a little bit straighter than mine. So basically what I do is I will take my starting point. We're going from 1 to 3. If we're going from 1 to 3, by the way, we would start from the left hand side of my rectangle. The left uppermost corner of the rectangle is going to hit the graph. So that's a left Riemann sum. So in this one, with this graph, now this isn't true for every single graph because sometimes it's going to depend on the concavity of the graph. But in this case, a left Riemann sum, you might notice that there's all these little, there's like little open spaces right here, and if we're going to 3, right here also. That means that this type of sum is an underestimate. I will tell you, this is a concave up graph. If it was concave down, the left Riemann sum would be an overestimate. But it varies based on the type of graph. So sometimes instead of doing a left Riemann sum, you're going to do a right Riemann sum. And you might be able to guess the right Riemann sum, we take the right corner of our rectangles, and that's what's going to hit the graph. So I wrote it out. The height of each rectangle comes from the right side. By the way, the words upper and lower mean in terms of like x values. So the height of my rectangle ends up being a higher x value in the right sum than in the left sum. This you might be able to see. I have like these spaces here. I'm overestimating my sum with this one. So you can see that neither the left or the right Riemann sums are perfect. They're both slightly imperfect. So then Riemann, when he was doing these, realized like, okay, well, left gives me one of them gives me an underestimate, not always the left, sometimes it's the right. One of them gives me an overestimate. So instead, he started doing what's called a midpoint sum. So I'll give you that on the next slide. So a midpoint sum, by the way, sometimes you're not always going to go by ones. Occasionally you'll go by halves, you'll go by twos. Sometimes you're going to even use different width rectangles. But if I'm just going by 3 rectangles, I'm going to go 1, 2, and 3. Those are going to be my cutoff points. So a midpoint rectangle would mean that I would start by, I would go to halfway between each edge of the rectangle, and that would be the height of my rectangle. So like this one would be right here. This next one would be at about 1.5. It would be right there. My next one would be at 2.5, so it would end up being right there. So you can see I actually have a little bit of excess stuff on that side. So the midpoint sum is a little bit better. You'll notice that I have an overestimate here, but an underestimate here, and it almost is going to, it's almost going to cancel each other out. This is a much better estimate than the left and right. So I'll write this out. This is a midpoint Riemann sum. Now, this is still imperfect, especially if your graph is, if you have kind of a weird graph, if it's not perfectly smooth, and you're rarely going to have a perfect graph. So an even better sum is, I'll show you this one now. So this one's probably the best estimate. And so the best estimate is what we call the trapezoidal sum. I'll go ahead and show you that. And for the trapezoidal sum, you're going to take, for each of the rectangles that you have, actually they're no longer rectangles, you're going to have your left side is going to be right on the graph, your right side is going to be right on the graph there. And so then we're going to draw it like that. So then, by the way, between 0 and 1 and 1 and 2, the left-hand side of 1 to 2 is the same as the right-hand side of 0 to 1. So then at 2, we're going to have a similar thing. At 3, we're going to have another similar thing. So it looks kind of like that. The trapezoidal sum is pretty good. It does give us a better estimate of the area. Another way to get a better estimate of the area is to draw more and more little intervals here. So either more rectangles or more trapezoids. So the more that you have, the better that you're going to get. That's where we're going. This is just kind of foreshadowing. We're going to get into using integrals to find those. An integral is going to be if there was an infinite number of rectangles. So that's just something to keep at the edge of your brain for later. So right now, we're going to do a few examples with Riemann sums. And in the future, we'll find that integrals are going to give us a much faster way of doing these. So I'm going to start by giving you the formulas for the left and right Riemann sum. These are really complicated looking formulas. You probably noticed that. If you take a college calculus class, this is most likely the way that you're going to see them, and you probably will see them with no explanation. So I'm going to give you the explanation of them now. So what we're going to do is I'm going to explain the formula, and then we're going to do an example both using the formula and not using the formula. So this thing L sub n, you might be able to guess that L stands for left. So L sub n means your left sum. R is going to be the right Riemann sum. I'm not writing out the word Riemann just because it's long, but you can write that in there. So n is going to be the number of partitions, or in this case, rectangles. You often hear them called partitions. And that's the same for both left and right Riemann sum. This delta x, remember that's the letter delta, is going to be the width of your rectangle. In this one, this f of x sub I minus 1 is going to be the length of the rectangle. The length, or you can think of it as the height of the rectangle. So I'm giving you a little bit of stuff, but it probably still doesn't make a lot of sense. So I'm thinking once I go over it, hopefully it'll make a little bit more sense. If you're still looking at this after we go over it, if you're still looking at this formula and you really have no clue what's going on, you don't actually need the formula. You just need to be able to find, you just need to basically be able to find the areas of a bunch of rectangles. Okay, so let's do an example. So for my first example, we are going to be estimating the area bounded by y equals x squared, the x-axis, and the lines x equals 0 and x equals 1. I told you to use n equals 4. Sometimes they'll tell you to use 4 partitions. Other times you'll have to use like 2 partitions. Sometimes you'll use 8. What you will find is the more partitions you use, the closer your answer is going to be to the actual right answer. So if you can, on this type of problem, the first thing you're probably going to want to do is draw a picture. That's usually going to be the most helpful thing. I know that we're going from 0 to 1, so I'm actually going to draw it like majorly zoomed in. And the other thing I know is that the graph of y equals x squared has, it has a point at 0, 0, and it has a point at 1, 1, and it's a parabola. So it kind of looks like this. So this is a good, nice zoomed in picture. It'll help you to do a closer up picture as opposed to a further away picture. It does go out that way too. By the way, it's not drawn to scale, as you can probably tell. So the next thing I need to figure out is my shaded area. What's it going to look like? And so I know that I'm going to end right here at that green line there. I also know that I'm going to divide it up into 4 partitions. That means that I am going to go by fourths. And I think I said this earlier in the video, but please use a calculator on these unless you really, really like working with fractions. So I think it's a good idea to draw what your Riemann sums are going to look like. So let's start with our left-hand one. For the left, what that means is like the first one, believe it or not, is just going to be a straight line. There's going to be no rectangle at all there. The second one's going to look like that. The third one looks like this. And the fourth one looks like that. You might be able to tell right away that this is an underestimate. So there's 2 ways to do it. Like I said before, you can either use that formula or you can just find the areas of these rectangles. The first thing to figure out, first of all, we know that n is equal to 4. That's the first thing we figured out. The second thing is figuring out what is this delta x. So the delta x is our width. Each of these, thankfully, has the same width. They're not always going to have the same width, but in this case they do. So delta x is going to be the distance along the x-axis between each of these. In this case, delta x is 1/4. So then the last part of this that I think is confusing for people is that that x sub I thing, or f of x sub I. So let's go ahead and work that out with the formula. So I'm actually going to write this whole thing out. I know that n equals 4, so I'll just write everything out. So I have f of x sub 1 minus 1 is 0. Plus f of x sub 1. Oh, sorry, these are all times delta x. And f of, so this is my term when I equals 1. You'll notice that I have f of 1 minus 1, which is 0. My term when I equals 2 gives me f of x sub 1. Then I have that, and so I get this whole thing when I write everything out. If you're confused about how I wrote this out, you can let me know in class, or like I said, there's a few ways to do these problems. I think I went through my entire AP Calculus class, and I didn't actually know it using the summation thing. I still got a 5 on the exam, but so if you understand what we're doing, I'd rather you kind of understand the idea, but if you can understand what the sums mean, that's even nicer. Okay, so I think the thing that people might get the most confused on this is what is this x of what is that x of 0 and x of 1 and x of 2 and x of 3 mean? Those things are going to be the x values of the that are going to appear on a graph. So in this case, this is x of 0. This is x of 1, it's 1/4. This is x of 2, 1/2. This is x of 3. So we have all of our possible x values. Like it's going to be the subscript of that is going to be, so like this 3/4 is the third point that we have on our x values on our graph. X sub 4 doesn't appear in this equation. It's going to be equal to 1. However, it will appear in our next one when we do the right Riemann sum. So, all right, let's go ahead and go through this. By the way, we already said that delta x is 1/4. You're welcome to bring that out front. So I'm going to pull the 1/4 out front. Then I am going to have so x sub 0 equals 0. So then I get f of 0 plus f of 1/4 plus f of 1/2 plus f of 3/4. You can evaluate those f values. Remember, this is y equals x squared. You can just evaluate them by substituting them in. I'm not going to do all of the calculations here. They are pretty unpleasant. You do get like a bunch of really big fractions. But when you do this, you hopefully you can try this on your own. You end up getting 0.21875. This is my left Riemann sum. Now, I did say that there's other ways to do this. So the other way that you can do this problem is by just finding the area of each of these things individually. So for example, I know that at x equals 3/4, my y value is going to be 3/4 squared, which is 9/16. That 9/16 is the height of this rectangle. You will find that the area of that one is 9/16 times 1/4. Believe it or not, that's actually the same thing that you get at this part of the graph. This ends up being 9/16 here. But so what you can do is you find each of those little areas, you add all three of them together. You might notice that's the exact same thing that I just did, but it might be more intuitive for you to try it using the rectangles. So then the right Riemann sum, I'm going to go ahead, I will draw it on the same graph, but I'm going to use a different color. So the right Riemann sums, I'm going to do it in blue. Almost the same idea. You're going to be finding all of these rectangles and then adding up their areas. The only difference with the right Riemann sum is that you're going to get probably a much higher number. And for me, it looks like it's almost double the number. Maybe not that much, but it's going to be pretty high. So we're going to do 1/4 my delta x. I'll actually show you how to write this out using the summation notation for this. So I'll show you a little bit differently. So I have this formula right here. Remember, n is 4. We already know that delta x is 1/4. So you can write this as 1/4 times this whole entire summation here. And when you do that, you're going to get 1/4 times f of, so the starting point on this one is going to be x sub 1, which is going to be f of 1/4. So you can actually do that with all four of those. So you do f of 1/4 plus f of 1/2 plus f of 3/4 plus f of 1. When you do that, you multiply it by 1/4 in the end, and you end up getting your area of all four of those rectangles added together. You can try it on your own if you want, but your area in the end should be 0.469-ish. So feel free to try that. We're probably not going to be doing a ton of really, really long problems with a lot of fractions in here. I'm not testing you guys on like how well you are at fractions, but I do want you to understand the idea behind this.